Hi, geometry students. It's me again. This is going to be the second video to the series of videos on the Pythagorean theorem and its converse. And if you take a look at what's on the screen right now is the definition of the Pythagorean theorem and the formula itself. We're going to be using that to find the lengths of missing sides and also to prove that a triangle is a right triangle and not an imposter by using Pythagorean triples. And so here we have Pythagorean triples are three numbers that always work in the Pythagorean theorem. You always plug in the biggest number for C. Why? The hypotenuse is the longest side. Common Pythagorean triples are the numbers 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, and 25. There are others, but these are just a few. You multiply any of these common triples by the same positive whole number, and it will produce more sets. Okay, here at the bottom, I'm just kind of showing you, I've plugged in 5, 12, and 13 into the Pythagorean theorem. Remember, you always plug in the biggest number for the hypotenuse, or for the C, which is here in this case would be 13. And 5 and 12, you just plug in as A and your B. You get 25 plus 144 equals 169. If you add 25 plus 144, it actually equals 169. Bada bing, bada boom. It worked. Okay, so here in this question, they said determine if each of numbers form a Pythagorean triple. So these lists of numbers have to be plugged into the Pythagorean theorem. Remember, always plug in the biggest number to the C. And then if the sum of the squares is equal to the square of the longest side, then it is a Pythagorean triple. If it doesn't, then it's not a triple. So let's go ahead and try it out. I'm going to start with letter A. So we're going to plug in 7 squared plus 8 squared equal to 9 squared. And we're going to get 49 plus 64 equal to 81. Obviously, if you add 49 plus 64, it's going to be bigger than 81. It's not going to equal 81. So in this case, right, that would be that 113 does not equal 81. Then we're going to say no, it's not a triple. All right. In letter B, we're going to plug in 21 as our A, 28 as our B, and then 38 as our C. Okay. When we square this, add it, we're going to get a total of 1,225. When we square 38, we're going to get 1,444. So obviously that's not going to equal. So we're going to say, nope, this is not a triple. In part C, we're going to plug in 15 as our A, 20 as our B, and 25 as our C. 15 squared plus 20 squared gives us a total of 625. When we square 25, it also gives us 625. So in this case, we're going to say, yes, this is a winner. It's a triple. Okay. All right. And so that's how you check to see if a set of three numbers is a Pythagorean triple. Well, we can also be asked to look for the lengths of sides of a triangle when you're given a set of numbers here, and then by classifying the triangle appropriately. So what does that mean? Okay, so let's go back over here. Here we have the converse of the Pythagorean theorem, okay? And in the converse, it states that a triangle is a right triangle if the Pythagorean theorem holds. That means that a squared plus b squared is equal to c squared, and there has that the triangle will be a right triangle, which means that it will have a right triangle. Sorry, a right angle in the triangle. If c squared is less than the sum of a squared plus b squared, then instead of having a right triangle, we have what we call an acute triangle. All right. If c squared is greater than a squared plus b squared, then what we'll have will be a obtuse triangle. Okay, so you're probably thinking, okay, well, how are we going to figure that out? Well, we are going to use the Pythagorean theorem. We're going to look at a list of numbers and plug them in. Always remember to plug in the biggest number into the C. Okay, so here we have, let me move this back over here. We have the numbers 4, 5, 6. So we're going to plug in the 6 into the C. So let's see, 4 squared plus 5 squared equals 6 squared, right? 4 squared is 16, 5 squared is 25, 6 squared is 36, right? If we add 16 plus 25, we get 41. 41 is actually greater than 36. So let's go back to our list over here. If the c squared is equal to the sum, then we have what we call a right triangle. If the c squared is less than, then we have what you call an acute triangle. If the c squared is bigger or greater than, then we have an obtuse triangle. So here, the c squared is less than, right? So therefore here, we don't have a right triangle because it's not equal. We have what you call an acute triangle. Okay? Let's try part B. In part B, we have the 12 is going to be our C. So let's see, C squared plus 8 squared equals 12 squared. We're just checking. 7 squared is 49. C squared is 64. 12 squared is 144. Okay, if we add the sum of 49 plus 64, we get 113. We want to know, is 113 greater than 144 or smaller than 144? It's actually smaller. So that means that the c squared is greater, right? So if it's greater, then this means that in this case, we have what you call an obtuse triangle. Okay? In example C, we're going to do this, we're just going to do the same process. 16 squared plus 30 squared equals 34 squared. Sorry, this is a 30, right? When we square and add, we get a 1,156. When we square 34 squared, we get 1,156. In this case, both the left side and the right side are equal. So here we're going to say we have a right triangle. Okay. Now let's take a look at letter D. Letter D, same process, except that now we have square roots that we're plugging into the Pythagorean theorem. Don't be afraid of that. It's super simple to simplify. I'm going to show you. All right, so in this case, though, what is the A? What is the B? What is the C? All right, and you have to use your common sense. The square root of 16 is actually equal to the number 4. Which means that it's going to be greater than the square root of 11 and the square root of 7, because the square root of 11 is going to give you a smaller value than 4, and the square root of 7 is definitely going to give you a smaller value than 4. All right, so then that means that we're going to plug in square root of 7 as our A, square root of 11 as our B, and square root of 16 as our C. Okay, now notice, don't forget to put the square or outside of the parentheses. Now, in the simplifying radicals videos, I mention that if you multiply the radical times itself, it simplifies to just the number inside of the radical. So here in this case, square root of 7 squared is actually just going to give you 7. And square root of 11 squared is just going to give you 11. Okay, and here square root of 16 squared is just going to give you 16. If we add 7 plus 11, we're going to get 18. And then we have 16 here. 18 happens to be greater than 16, but the 16, that's the c squared part, right? So which means that this is less than. And because it's less than, then we're dealing with an acute triangle. Okay? If you need to go back and review that example again, just so that you can understand what's happening when you're squaring a square root and when you're raising it to the second power. Okay? All right. Okay, so here's example 4. Find the side x. Leave the answers in radical form. So we're being asked to find the missing side by using the Pythagorean theorem. This is really simple, right? But we have to identify where our c is. Our c is always across from the 90-degree angle. So here in this case, c is 14. So we're going to plug in x squared plus 11 squared equals 14 squared, all right? And we'll simplify x squared plus 121 equals, let me look at my cheat sheet over here. I'll use my calculator. 14 squared. Let's see. 14 times 14 is 196. Subtract 121 from both sides. Minus 121 equals 100 and, wait, that's not correct. 196 minus 121 is 75 equal to x squared. Okay, now in the instructions, they told you leave answers in radical form, right? That does not mean that we're going to leave the answer with the 75. We're going to actually have to simplify this. But first, we need to get the x by itself. So we're going to take the square root of both sides. Okay, so this is going to give us x is equal to the square root of 75, right? In the simplifying radicals videos, we learned how to simplify 75 by using fractal tree. So we're going to break this down, all right? And we're going to break down the 75 by dividing by 5 because it ends with the number 5. So 5 times 15 is equal to 75. And we're going to break down 15 into 5 times 3, all right? And here we notice that the 5s are repeating twice. So that means that we're going to be able to take out a 5. And then this 3 that remains is going to stay inside of the radical. So then our final answer is going to be 5 root 3, which means that this leg labeled x has a value of 5 root 3. Now, if you wanted to, you could actually check to see if this is correct. Okay, so in order to check, you go back to the Pythagorean theorem and plug in the 5 square root of 3 back into the problem. So let's do that. 5 square root of 3 squared plus 11 squared plus, sorry, not plus, equals 144 squared. All right, so let me go back up, make sure I plug that in. Okay, cool. So then simplifying the left side, this 5 square root of 3 squared is going to be the part where some of you might think, well, how do you do that? So the way that you do it is it means that you're multiplying 5 squared times square root of 3 squared. Okay, now over here, we're still going to have 121 equals 196, okay, from before. And over here, we're going to go ahead and square 5 squared gives us 25. And if we apply that little trick, the square root of 3 squared is just going to give us 3 plus 121 equals 196. Okay, we're going to multiply 25 times 3. That's going to be 75 plus 121 equals 196. And guess what? If we add 75 plus 121, we get 196. Bada bing, Bada boom. There it is. We got it. It checked, which means that the value of x is 5 square root of 3. Good job. We did that very, very well. I'm going to go ahead and stop the video here, and then let me know how you found this and if you understand it. If you don't, I need to do more examples, then I will.